Oh, I need to drop the VPN too. All right, while you guys are working, I'm just going to try to narrate the video since I screwed up and forgot to hit start stream. That's why I need a producer, but that'll never happen. Okay, so quick recap for the online folks. Again, I apologize for being late to the game, but we're currently working on our multivalent metals. And so these are ones with variable oxidation states, such as our transition metals and some of our P blocks like lead, thallium, and tin. And we had just gone over this copper oxide example. So balancing our oxygen 2 minus, writing out our equation to solve for copper being 1 plus versus our CuO, where the copper has to be 2 plus. This was just historical naming facts, not important. And now we're doing these examples. So let's see how we're doing with these. So let's kind of walk through them together. So what's our oxidation state of chlorine normally in a compound? Yeah, -1. I saw people say it loud. And yeah, make sure it's -1, so good. So -1, and then, right, we can do our algebra. So -1 times 2. So what does our iron need to be to balance this out? Excellent. So now we have iron 2, and now we can just name it chloride there. Any questions on that one? Yeah.
And should we make sure we're writing in Roman numerals?
Yeah. Yeah, it has to be in Roman numerals. All right, let's look at the next one. So then, what's this one then? Good. So iron 3 chloride. And again, same process, right? Base it off of the chlorine. So -1 times 3, -3 totals. And then again, so far we're just working with neutral compounds. So yeah, excellent. Iron 3 plus. What about this one here? So double check it, because what's the oxidation state of oxygen? So 10, 4, and make sure you use the proper Roman numerals. Oxide. And then what about this last one? Excellent. So cobalt 3 nitride. Oh, let me rewrite that R. And then just kind of burn this into your brain a little bit. So for some reason, I've noticed students tend to like blank out if they see nitride or phosphide, arsenide later. But just remember that's your elemental of these. Any questions about those there? Yeah. Well, again, your periodic table is not all inclusive, right? So there, like I'm saying, your metal can be like any oxidation state. You can have cobalt 1, cobalt 4. Yeah. So yeah, those are typically the most common ones, but cobalt can do all sorts of oxidation states. But yeah, we won't go down the full rabbit hole of oxidation states of metals. Plus, like that's like literally what researchers want to do in chemistry is like get a new oxidation state or get like a rare one. So that's why the Roman numeral is way better. It's because we don't know. We have to base it off of the compound it's in. All right, so now let's work on polyatomics. And admittedly, I forgot to print this out. So I'll have to print out your cheat sheet. We'll call it probably for Monday, unless you guys stick around. I can do it after lecture while you guys are quizzing and grab some polyatomics. But our polyatomics, so basically these are just covalently held compounds that have a charge on them. For example, so we could just look at, we'll start with something simple like hydroxide. And so hydroxide would be like so. Let me count my electrons. So we have our hydroxide here, negative charge on our oxygen. And so again, right, our polyatomics just have a charge. Let's look at another one. So we'll get into how to draw all these out. So let's draw out ammonium. So again, just a covalently held together ionic compound. And so like I said, I'll give you a cheat sheet. I don't expect y'all to memorize them. I'll also point out a few common ones. So we'll definitely see hydroxide, right? We saw it in lab, if you were in lab, with our demo of reacting our alkali metals and water, right? So we said that that was our product of lithium hydroxide. So we can rewrite that reaction. So again, just thinking about when we will see these. So this morning we did lithium, and I'm going to write water like this so we could see the double displacement. And so then we make lithium, oops, I don't need two equivalents. Lithium hydroxide. So again, just making this species in solution. Other common ones that we'll see a lot. So we have nitrates. So we'll see a lot of nitrates in this class, or you may have already, I don't remember what your salts were this morning, but nitrate is a pretty common salt. What else? Oh, okay. We should point out what a peroxide is. So the peroxides are kind of confusing because this is one of the only times where oxygen has a -1 oxidation state. So you can see the entire peroxide is O2, right? But then the entire peroxide has a -2 state, such that each individual oxygen is -1. So that's kind of confusing. I'm pointing it out because we typically base our oxidation states off of oxygen, but then you just have to be careful that it's not a peroxide. And then the structure for a peroxide, so I'll just write like hydrogen peroxide, is just anytime you have two O's bonded together, so then that's going to be your peroxide. And you can abbreviate it like so. So these R's just mean like any organic group. So it could be like a methyl. I think you can even have like nitrogen-based peroxides. But again, anytime you see this oxygen paired with itself like that, that's a peroxide, and that has a -2 charge. And then we'll probably see carbonates, or if we haven't already, it's definitely coming up. I want to say next lab. I kind of forget which order your labs are in. Sulfate, you'll also see a lot. That's a very common salt. And then phosphate, we'll see that. And then notice that ammonium is one of your few cations. So, right, all of these were negative for the most part. And then we have ammonium, which has a positive charge, so that's a little odd. And then any sort of ammonium derivatives, not to go to drugs, the class immediately, but like methylammonium comes to mind. Or, so that would be related to methylamine, which obviously makes meth because everything makes meth. Uh, but yeah, they tend to be ammonia-based compounds that are positive. And then they threw in mercury, but I mean, I really wouldn't have done that personally. But and then other ones that confuse students. So we probably won't see acetate quite yet, but it will come up in our last week of our acid-base chapter. And then it just confuses people because sometimes they write it in this form, right, where it's carbon, hydrogen, oxygen, so C2H3O2. Or it's sometimes written out as a CH3COO. And they're used interchangeably, so you kind of have to just like recognize it in any form, which most students find kind of frustrating, but just kind of be aware of that. So yeah, I'll print out a cheat sheet for y'all later. And so let's try to name these. So probably let's just copy them down first, and then I'll scroll back up so you can refer to the polyatomic names. And then how we name them, sorry, let me let you copy that. But it's pretty easy. We just name our cation metal appropriately. So right, in the case of potassium, magnesium, we can just state them, right, because they're group 1 and group 2. For iron, you'll have to determine the oxidation state, right? But then we'll just write it out normally, iron whatever. And then we just name our polyatomic. So going back to our lithium, right, that's why we just said it was lithium hydroxide. So you just name your polyatomic. All right, did everybody copy the examples before I scroll up? All right, so now see if you can name them based off of our sheet. And that's also why this class is open note. That'd be kind of painful. I had to do that back in Gen Chem back in the day, name all these. And if I need to scroll back down, just let me know. So I'll give you guys a few minutes to look at that. All right, what do we get? So what do we get for our first one then? What's its name? Yeah, go for it. Excellent. Potassium dichromate. Any questions on that one? So remember, potassium is our group 1, right? So it's always, always, always going to be +1. So then, right, when we know the oxidation state, we don't have to name it. Yeah, so, and then, you probably would, yeah. Yeah, because it's part of like the naming convention. And then, what about the next one? Excellent. So magnesium hydroxide. And again, same thing, right? We know that magnesium is a group 2 metal, or you could look at it, right? So, okay, find magnesium on your periodic table. Group 2, alkaline earth. So we know it's always, always, always going to be in that 2 plus oxidation state. And then that's how you would, go back and forth between our name and our formula as well. So what about this one? So we did have to determine, right, the oxidation state of iron. And iron 3 nitrate, excellent. So iron 3, and again, just a quick recap, right? The first thing I would do is look at your nitrate, right? It's -1, so -1 times 3. So then we know we need 3 plus to balance it. Not too bad. Any questions about those? Yeah, so typically they're anions, right? So they all tend to be negative except for, like we said, ammonium, right? But we could practice, right? So then how would you name? So that was based off of the oxygen, right? So then you go back to oxygen is -2, and then there were 2 oxygens, so that's where you did -2 times 2 is -4, or yeah, it's -4, so then you needed a +4. But yeah, you won't see like a +1 and like another metal. Well, not typically. I shouldn't say that, but yeah. I didn't think so. I don't know. I'll have to look at it then, but yeah, I didn't think that that would be on the week 2 quiz, but we can look at those details later. Sorry. So then, how would we name this one here? Yep. So ammonium chloride. Excellent. And so that one, again, was pretty straightforward, right? We can just name our, in this case, polyatomic cation, and then chloride. And so here's the cheat sheet that, like I said, I will have this printed out either later today or Monday. All right, so now we want to practice kind of going back and forth. Let's see, let's try to go the opposite way now. And so let's just start with the first one and see how it goes. So see if you can determine the correct formula. And again, we have to make a neutral compound. So what did we get for our formula for this one? Uh, well, let's just start. So what's our oxidation state of vanadium according to this? So +5. And then what's arsenic's or arsenide's oxidation state here? Not +3, but yeah, -3. And so now we have to, again, make this neutral. But this is where we could do a little trick. So this is called a swap trick if you've never seen this before. So what we're doing, right, is we're trying to solve the algebra, but we have two variables, right, because we have x and y, because we don't know how much. So technically, we have 5x plus -3y gives us 0, right? So the easiest way to solve them is to plug in 3 for x and 5 for y, right? And then that balances out the charge. So I like doing this swap trick. So now we drag the 3 down there and the 5 down here. And then you double check that it's in the simplest ratios, but we'll kind of look at some caveats where this swap trick goes wrong. So you just double check yourself. And so we should have gotten B3AS5 for this one. Yeah, because we need the proper formula now for our ionic compounds. And so we're just trying to balance it, right? So if we have our vanadium 5 plus, we need to, yeah, get them to be neutral. Yeah. No, because we're writing our formula now, right? So it's just how many atoms. Mm-hmm. So yeah, and right, we could kind of rewrite this visually. Is what we're saying is okay. We have 3 vanadiums hanging out that are at a 5 plus oxidation state, then, right? Versus 5 arsenics that are 3 minus, and then is that neutral? One, 2, 3, 4, 5. Right, so now we have 5 times 3, so that gives me positive 15, and negative 3 times 1, 2, 3, 4, 5. So negative 15, and if we wanted to take this a step further, oops, I did not want to open my Xbox account. But we can, right, again, it's just a ratio. Arsenide, sorry, I can't spell. Let's see if we can find a cute picture. Oh, come on. Now I can't find what I was looking for. Well, maybe this is not a good example. But I was just trying to show is like they would be in that ratio, right? Like, and again, this is not a discrete formula, but just again, they're repeating structure. Maybe this is like, I don't know, that's weird. Well, here's vanadium nitride, a crystal structure of that, which is again electronically similar, right? So it's just repeating units, repeating units. So it's this crystal lattice structure of that in that 5:3 ratio that we just determined. All right, so let's try a few more. Let's go back to these for a second. Oh, let's mention a few things. So I didn't talk about this example yet. And so this is kind of a funny one. So we have this H attached to a metal. So this is like a metal hydride. And so that's how to name it. So I'll just give it away. So we have sodium hydride. And this is a little funny because hydrogen in this case is actually a -1, which is not very typical unless it's bound to a metal. So otherwise, hydrogen is typically 1 plus, but with these hydrides, so you have like aluminum hydride, for instance, and then these compounds tend to be pretty flammable, some of these metal hydrides. But so then this would be aluminum hydride if we're naming hydrides. All right, other things that we haven't talked about naming yet. So let's see. I think I have it somewhere in my notes, or I thought I did. And so the other thing that we might see is sometimes there are compounds that are complex to water. And so that's what this is showing here with this little dot. And so it's showing us that it's complex with 7 waters. And so here's how to name those. And so sometimes you could have one water molecule bound to like 2 of something else. So that's where you would get this hemi. So hemi-aqua compound. And then we call our ending hydrate, right? So it's like hemihydrate, or monohydrate, or dihydrate, hexahydrate. So depending how many. Or if you had 1.5, which I don't have a good example, but there's sesqui. But otherwise, it's your normal prefixes, right? Di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And I'll show a quick example again, because we just want to appreciate that, yes, it's actually complex to it. And so it does change the properties. Of course, Wikipedia seems to be our most reliable. Come on, load faster. There we go. And so I like nickel because this is one of the ones where they're very clearly distinct. So we have the hexahydrate complex, and you can see right the formula is shown here. So they're both nickel 2 chlorides. It's just the hexahydrate is this green color, and then you can purify it. You can actually get off the water. So the common purification method is you can reflux it in like toluene. And then after that, you get this nice anhydrous powder, which is now the anhydrous form, right? So no more waters on there, nickel chloride. So that's kind of cool. So going back to this one, let's see if we can name it. So, right, I might have to show you some polyatomics, or I might have to print out a sheet eventually. So we're looking at, might see if you can find SO3 there. Hint, hint, right? So look at what that is. And then how would we name this last part of our water? So come up with our name here. So then we'll name the first one. So excellent. So beryllium sulfite, right? And then hepta for our 7 hydrate. So let's try a few more of these. So let's do number 5. See if you can do 6, and I may have to pop over. And we'll try 8 for now. And if you need me to pop over to the chart, I can. So yeah, do we have, so Fe3PO42 written down, this written down. I gotta be careful, else I'll just say the names. So I'll give you guys, so copy these down and then I'll flip back over to our polyatomic. Then if I need to flip back, I can. I'm trying to find which one's better to see. No, like this. The point of this class is not memorization, right? So you will have open notes for everything. So like I said, I will print this out. We'll finish up in the next 5 minutes or so, uh, and I can print out the cheat sheets. But yeah, I don't want you guys memorizing stuff in this class, right? That's not the point of the class. We're only here for 10 weeks, so there's you would be so stressed about memorization. Yeah. So let's try to go over these. So what do we get for this one? It should be iron phos. Check the ending again, but then we're missing something. So iron phosphate. But then we have to determine our oxidation state, right? Don't forget about that. Iron's our transition metal. So what's our oxidation state? I think I heard somebody say it. And so this is, while you guys are marinating on it, this is a good time to introduce what I call the reverse swap trick, and we can check it out. So I'm just seeing if this pencils out. So right, I bring my 3 up, I bring my 2 up, and then you just want to double check that is phosphate really 3 minus, because sometimes when we do this reverse swap trick, especially with like the tins and the oxygens, we'll find out is that it kind of fails us. But in this case, it works out, right? So phosphate is -3. So then just kind of double check yourself. Well, -3 times 2, that gives me -6. So then reversing out, what does iron have to be? Which you guys whispered it. 2. So iron 2, phosphate there. And then what about this one? So this was tricky just because we had a lot of polyatomics in there. Yep, so ammonium acetate. So good job recognizing this. Again, students always get tripped up by it, including my 200 level students. So don't feel bad, right? Oh, that's the other thing about chemistry. Again, you're learning a language, you're reading. It just takes a lot of time and a lot of familiarity. So yeah, so that's like the tricky part is you have to kind of recognize like where's your cation and where's your anion part. But that's where hopefully when I print out the sheets that'll also help with that. All right, let's look at 8. So again, this is another tricky one, but I think reverse swap trick would help. So what's our name here? Oh, watch. What's it would be 7, but what's the compound? Manganese. Manganese. Otherwise, they'll think you're saying magnesium. So manganese, and then yeah, 7, which again, double check the math that our swap trick worked. But okay, -3 times 7, that's -21, and 7 times 3 is also 21, so perfect. So manganese 7. Yep, so phosphate again there. All right, that looks good. Let's see. Might want to do just a few more really quick, even though I said I was going to end lecture. So try nickel sulfate at least really quickly. And so Ni2 and then sulfate. So SO4, 3. So that looks good. Again, just double check yourself. So 3 times 2 is 6. Sulfate is -2, but again, let's go back to our sheet. So yes, sulfate -2, and then -2 times 3 is -6, so that does work out. And then if you want more practice with this, so you can see that I shamelessly stole these from another community college. And so if you wanted to like go through all these and check the answers, you could probably find them there. You could also like bug me, email me. We could also keep working on this next week. Oh, other things I should mention. I forgot to talk about acids. So this will come up. So I feel like unfortunately for the acids, you just kind of have to learn them. Like there's not always a rhyme or reason. Like you have hydrobromic, hydrocyanic. I mean, hydroiodic follows the same. I don't know why they didn't put that on there. So hydroiodic acid, hydrofluoric acid, right? HF, hydrochloric. But then we also have other ones like nitrous acid with our OS. And yeah, I mean, typically you guys probably won't see nitrous acid in practice. You will see nitric, so HNO3. But again, it's like I feel like that's more of a memorization thing. Phosphoric acid we'll see in practice likely. So that's H3PO4. But again, I really don't have good tips on like how to memorize these other than you memorize them. You won't see sulfurous in practice really, but you might see sulfuric, or at least I'm just talking about basic Gen Chem. We're not going to worry about all those perchlorates. All right. Before I actually stop talking for the day, I just wanted to go over one little part on your lab because there's kind of a tricky part on there. And it's with these calculating the abundances problems. So let's look at, I'm just going to pull up this magnesium example. And if you turn in your lab and you want to redo it or something, I can always give it back. And I am behind on grading labs. So I have like everybody's lab. I just haven't like graded them yet. I need to hide in a hole for a second. All right, so let's go through this. So I think we had kind of talked about the isotope concept, right? That the mass on your periodic table is an average of all the isotopic masses. And so the only tricky part to these is to be consistent with the sig figs. So to go through this properly, you have to do it kind of step by step, right? Following your sig fig rules. So we have 23.985 AMU. So that's a 78% abundance. You can multiply it by 0.7899. And then plus, so our next one is 24.986 at a 10% abundance. So right, move your decimal over to 0.00. Well, yeah, let me go through it. So when you do these, and you do the multiplication step, right, you keep 4 sig figs because your abundance was only reported to 4. So let me pull up my calculator real quick. Yeah, because you have to multiply it. You have to convert the percent to a decimal, right? So yeah, so let's go through. So then we'll punch it in. It would help if I punched in correctly. So times 0.7899. And so again, write that to 4 sig figs. So that'd be 18.95 for rounding. Then keep going. So then 24.986 times 0.1. And right, I'll leave the zeros off, but we know we still need a report to 4. So 1, 2, 3. So I'll round that to 9. So 2.499. And then the last one. So 24.983. Oh, sorry, thank you. 25.983 times 0.1101. So again, 4 sig figs, 1, 2, 3, 4. So I round that to 2.861. So now we do this addition, right? And then addition rules, well, we report to the least number after the decimal point. So that means we can only go to 2 after, once we're done adding, right? So now let's add everything up. And so let me use my actual numbers. So 18.95 plus 2.499 plus 2.861. And so that gives us, and it just so happens that it worked out, but that would be 24.31 And so we don't need to round any further, but we wouldn't tack on a 0 or anything, right? So again, we can only report it to 2 after, so 24.31 there. So just watch that. Some of them are tricky, and I feel like you lose numbers, but it is what it is. You're given what you're given, so just kind of roll with it. So specifically thinking of this antimony one, right? You only have 3 decimal places there, but again, just go with it step by step, right? So do the multiplication, then do the addition, keeping your sig figs straight at each step. All right, we'll end there for today. So I do have the paper quiz if people are taking the paper quiz in here. Otherwise, right, use this time to catch up on, right, fixing the labs or doing whatever, asking me questions. I'm here. Yeah, otherwise, did I open up the quiz online? I don't remember. Because I'm also running 2 sections. I'll make sure that it's opened up on the in-person one, the quiz, if you guys want to take the online version. You could also take both and then fix your grade later if you score higher in one of them. I don't mind. Just
For this one, do you think that it would be the same if I just moved the decimal over twice?
so this one you can only report to 2 sig figs, so that's what's kind of nasty about that one. So you have to do it like step by step, right? Because this one you get 2 sig figs. So I would have to work it out myself, but all right, I think I opened up the quiz online as well in this section, so you could take it online. Otherwise, I will hand it out. Then if there's any questions, yeah, questions, just let me know. Otherwise, email me.